Hi, I'm Rudy, and I'm presenting the paper Structural Iterative Rounding for Generalized K-Median Problems. This is a joint work with Anupam Gupta and Ben Moseley from Carnegie Mellon. So the first thing I'll do is I'll define the basic K-medians problem, then I'll define the particular variance we study. I'll state our improved approximation results for these problems, and then I'll hopefully give you a few of the main ideas how we achieve these results. So let's begin just by defining the most basic K-median problem. In the K-median problem, we're given a set C of clients, which I'll represent by these blue points. I'm also given a set F of facilities, which I'll represent by these red points. And further, I'm given a parameter K, which is the number of facilities I'm allowed to open. So in this example, I've chosen K equals 2, and I've chosen these two green points as my open facilities. So what is my goal in opening facilities? I want to open facilities in order to serve clients. In particular, I want to minimize the following objective function. So for every client, every blue point, I find its closest facility, so its closest green point, as shown by these arrows. I'll sum out those distances across all clients, and this is the objective I want to minimize. So this is the basic K-median problems. Now let's talk about some K-median variance, which we'll study in this work. So how can we generalize K-median? Well, we can place different constraints on the clients and facilities. For example, in the knapsack median problem, instead of opening K facilities, now my open facilities must satisfy a given knapsack constraint. On the other hand, in the K median with outliers problem, instead of serving all clients, now I'm given another parameter M. I can choose M clients I would like to serve. I don't have to serve all of them in general. And the best approximation ratio for both these problems is about 7 by the iterative rounding algorithm of Krishnaswamy, Lee, Sandeep, KLS. So the main result in our work is that we improve on KLS for these two problems. In particular, for knapsack median, we improve the 7 approximation to about 6.3. For K median with outliers, we improve the 7 approximation to about 6.9. And further, we consider K median with a constant number of side constraints. So this is what we mean by generalized K median. So one can think of this as K median, but I have a constant number of knapsack constraints on my open facilities and a constant number of coverage constraints on my served clients. For this problem, we give a 6.3 pseudo approximation. So with the remainder of this talk, I'm going to describe the main ideas to achieve a 6.9 approximation for K median with outliers. The algorithms for the other problems are analogous, so the main ideas will be the same as for K median with outliers. To begin, let's just write down a basic LP for the K median with outliers problem. So recall in this problem, I can open at most K facilities, and I have to serve at least M clients. So in my LP, I'll always index facilities with I's and clients with J's, and I'll have two types of variables. Xij means I connect client J to facility I, and Yi means I open facility I. So for example, these constraints mean, the first constraint means I can serve each client with the facility only if that facility is open. The second constraint says I can serve each client at most once. The third constraint says I have to serve at least M clients. That's the outliers constraint. And the fourth constraint is the open facilities constraint. It says I can open at most K facilities. So you don't have to remember all these constraints in detail. I just want to draw your attention to the second one, which I've highlighted in blue, which is the constraint that can serve each client at most once. So let's think about solving this LP. Suppose we solve this LP and we get an optimal fractional solution. What does this blue constraint tell us? Well, it tells us the following. So just focus on any fixed client, a fixed blue point, and start growing a ball around that client. I'm going to grow that ball until I see all of the facilities the LPS decided to connect that client to. So all of the Xij variables that are non-zero for that fixed J. So for every client, I now have a ball of where this LP decided to connect that client. So we'll keep this idea in mind, and we'll write down a different LP for K median with outliers that is more towards our iterative rounding algorithm. So in particular, we want to write down a set cover type LP for the K median with outliers problem, so a different LP. So I've transferred the main ideas from the previous slide to this slide. So we just have the same constraint highlighted in blue, which is that I can serve each client at most once. And remember, we solved the LP to get an optimal solution. And we'll just look at this one client, this one blue point. I'm going to grow a ball around that client until I see all of the facilities the LP decide to connect that client to. This is the blue ball you see. And the red dots represent the open facilities. So we'll define this ball as to be ball J, which is client J's allowed connections. And now I can write down a different constraint. Instead of saying I can connect each client at most once, I can say I can open at most one unit of facility in each ball J on the right. Now, with these ball J's in hand, I can write down a different LP where I want to cover these ball J's using open facilities. And this is the LP we're going to think about. So there are a few things to note in this LP. Note that we only have variables, the yi variables for facilities. We no longer have xij variables. So let's just go over what all the constraints mean. So the first constraint says I can cover each ball at most once. Remember, we have one ball for each client. The second constraint says I must cover at least m balls. And the third constraint says I can open at most k facilities in order to cover balls. So what is this LP expressing? We're trying to solve the problem where we want to cover m balls, our ball J's, using k open facilities. Now let's think, what would we like to happen when we solve this LP? So this is our idealized world. So suppose we solve this LP and the tight constraints among these blue highlight constraints all happen to be disjoint balls, and those all represented by these green balls. So imagine I solve this LP, all the tight constraints are disjoint balls. What do I get from this? Well, actually, I can show that this solution only has a constant number of fractional variables. So the green dots are integral variables and the red dots are fractional variables. And the way to see this is to note that the tight constraints form a partition matroid intersected with a constant number of side constraints. So this is great. We have a constant number of fractional variables. For us, this is as good as an approximation algorithm because we can use known enumeration techniques to round the constant number of fractional variables at the end to get a fully integral solution. So keep that in mind. The goal for the rest of this paper is to get a solution with a constant number of fractional variables with good approximation ratio, and then we'll use standard enumeration techniques to handle the rest. So this is a nice idea, but what's the problem here? Well, suppose this was in our real world, we solved the LP, but the tight constraints don't form disjoint balls. Well, then what can we do? Well, what we would like to do is to modify the LP. We would like to modify the LP using iterative rounding in order to control the balls that become tight, so we can realize this idea of getting tight disjoint balls. So this is the main idea of iterative rounding. We want to use iterative rounding to control the tight balls. And let's see how we can do that. And this is how we're going to improve on KLS. So I've transferred the framework from the previous slide here. So what's the framework? Well, we want to solve the LP, the set cover LP. And if the solution has our desired structure, then we're done and we're happy. But what if it doesn't have our desired structure? Well, I'm going to modify the tight constraints and then repeat until we have the desired structure. So for KLS, as on the previous slide, this desired structure is disjoint balls. Why? Because if we have disjoint balls, we have a constant number of fractional variables. So in order to achieve disjoint balls, they have to modify the tight constraints as follows. So if I solve the LP and my balls aren't disjoint, then at least two balls intersect. So if two balls intersect, then delete the larger radius one. This will ensure that if there are no modifications to be made, we have disjoint balls. So for simplicity in this talk, I'm going to assume that the radii of the balls are distinct powers of 2. So to achieve powers of 2 by itself is not too hard. You can just discretize the radii. But the distinctness is with loss of generality, but it makes our modifications simpler. To remove the assumption, we just have to consider a slightly more complicated modification rule, but I don't want to get into those details here. So we'll just assume they all have distinct radii. So what does this iterative rounding procedure look like? So suppose I solve the LP, and I have tight balls that are intersecting, as in these two green balls in this picture. Well, the radii are distinct powers of 2, so one of them must be smaller by at least a factor of 1/2. And what's the modification that we're going to do, that KLS will do, is because these balls intersect, they're going to delete the larger radius one. So note that when we resolve, it could be the case that we delete this green ball still for another ball with half radius. And this can keep going on until eventually we have a desired structure of disjoint balls. So why is this okay? Well, the initial ball we were considering, the first ball that was deleted, had some radius, which we'll denote by red. And if we would like to connect it to facilities, if we'd like to cover this ball, we know due to this chain of deletions that we can find this one unit of open facilities at this final green ball that remains tight and stayed. We didn't delete this constraint, so we still have one unit of facility there. Why is this okay for the objective function? Well, note that every time we deleted a ball, the extra distance that our initial guy had to go decreased by half. So this is a geometric sequence. So in particular, we can bound the cost is a constant times the radius. So again, for simplicity, I'm going to assume the client connection cost is exactly the radius. In general, the cost of connecting a client can change because it can be connected to a closer facility in its ball or a farther facility in its ball. But we're just going to assume all the facilities in the ball are exactly at the radius. So again, this is with loss of generality. But to remove this assumption, we just have to consider a more careful definition of a ball that takes into account the different possible connection costs of a client. But this will still capture the main ideas. So to summarize what happened, the desired structure of KLS is disjoint balls. The reason is because this will give us a constant number of fractional facilities at the end. The modification is if two balls intersect, we should delete the larger radius one. The reason we do this is because we can bound the final cost of a client by a constant times its LP cost, its radius, let's say. So this gives us a constant number of fractional variables and a constant approximation. So this is where the approximation ratio of KLS arises. How are we going to improve on this? We're going to use the same framework, solve the LP, modify until we have the desired structure, but we're going to change the desired structure and change the modification. So now we're going to generalize the desired structure. Now, instead of allowing one set of disjoint balls, we're going to allow two sets of disjoint balls. Thus, we have to change our modification as well. Now, instead of having two balls intersecting and delete the larger radius one, now, if three balls intersect, we delete the largest radius one. So what effect does this have on the approximation ratio? So if we have three balls intersecting, as in this picture, and we delete the largest radius one, because the radii are all distinct powers of 2, now our initial ball, which we deleted, can go to a ball of quarter radius. So the extra distance we travel quarters at each step instead of halves, as it was the case in KLS. This is where approved approximation ratio arises from, and this is the main idea of our algorithm. We generalize the desired structure of KLS and thus generalize the modification. This allows for improved cost. So what are the technical challenges in this approach? Well, we've already changed the extra distance halving at each step to now the extra distance quarters at each step. This immediately gives us an improved approximation ratio. However, at the same time, we also went from one set of disjoint balls to two sets of disjoint balls. So one set of disjoint balls was nice because I could have a constant number of fractional variables. But now with two sets of disjoint balls, we can have unbounded number of fractional variables, as is in this picture, where the green balls are their tight constraints, and the red points are the fractional variables. So to get our final approximation algorithm, we have to find a way to reduce the number of fractional variables to a constant. And the main technique we're going to use to do that is to show that these extreme points, resulting from these two sets of disjoint balls, are actually highly structured. And we're going to use this structure to further modify the tight constraints and bring our solution down to a constant number of fractional variables. So what is this structure? So informally, our main structural theorem is that the two sets of disjoint balls form a constant number of disjoint chains. We're going to call this object a chain decomposition. So what is a chain? Example of chain is in this below picture. So in a chain is a path of type balls, these green balls. Each ball has exactly two fractional variables, which are these red dots. It shares one red dot with the previous ball along the chain and one red dot with the subsequent ball in the chain. And there's a constant number of such chains. Note that these chains can be arbitrarily long, so this gives us an unbounded number of fractional variables, but these fractional variables have a very nice structure, these chains. So now we want to use this chain decomposition to further modify the balls. So a lot has happened so far, so let's just recap and sort of summarize our whole algorithm now. So I've just transferred the framework from before, the iterative rounding framework, where first we solve the LP, then we modify the tight constraints, and we repeat this until our tight constraints have the desired structure. So recall, our modification is if three tight balls intersect, I delete the largest radius one. And this gives us the desired structure of two sets of disjoint balls in our tight constraints. And our structural theorem states that these two sets of disjoint balls actually just form a chain decomposition. So recall our goal. We want to get a constant number of fractional variables. But if magically after we solve our LP and have a chain decomposition, if we happen to have a constant number of fractional variables, then we're done. We have improved cost over KLS due to our quarter radii at each step over half radii, and we have a constant number of fractional variables, so we're done. It remains to consider the case if we have a lot of fractional variables left. Now, what are we going to do? The remaining work to do is we have to modify the tight constraints using in the chain decomposition. We want to use the structural properties of the chain decomposition to say we can do this whenever we have a lot of fractional variables. So our overall algorithm is we do the iterative rounding step where we modify the LP until our tight constraints have a chain decomposition. If we have a constant number of fractional variables, we're done. If we have a lot of fractional variables, we're going to do a further modification on this chain decomposition. And then we'll repeat this whole process until we have a constant number of fractional variables. Now let's see how we're going to use our chain decompositions to further modify the tight constraints. So what's our setting here? We're in the setting where we have omega-1 fractional variables. We have a lot of fractional variables. And we have a chain decomposition. So recall in a chain decomposition, there's a constant number of chains. So in particular, some chain must be long in our chain decomposition. In particular, this chain, you can imagine this chain just extends further outwards. Now, what's our modification? Well, we're going to go to the middle of this chain. Because all the balls have distinct radii, distinct powers of 2, let's look at the two balls in the middle of this chain. One of them must be larger than the other one, by at least a factor half. So we delete the ball in the middle with larger radius, and we're basically sending him to the ball with smaller radius. So in this picture, we send this blue ball to its neighboring green ball with half the radius. This is our final iterative operation using chain decompositions. Now we're ready to summarize our entire algorithm with all of our modification rules. So again, on the left is our iterative rounding framework. We solve the LP. We modify the tight constraints. If three balls intersect, delete the largest. And we repeat this until we have two sets of disjoint balls, giving us our chain decomposition. If we have a lot of fractional variables, a super constant number of fractional variables left, then we modify the tight constraints in the chain decomposition as follows. We know that one of the chains must be long because we have a lot of fractional variables. So we go to the long chain. We look at the middle of this chain. There are two balls. One must be larger than the other. We delete the larger ball and send him to his neighboring ball of half the radius. So we send this blue ball to this green ball. And then we repeat this whole procedure until we have a constant number of fractional variables. So at the end of this algorithm, we will have a constant number of fractional variables. Now it remains to argue about the cost. So let's do that, and this will complete our proof. So how does our final approximation ratio arise? Well, there are two types of iterative operations our algorithm makes. The quarter step in the iterative phase, where I have three balls intersecting, I delete the larger radius one. We call it a quarter step because the blue ball has a neighboring ball that's still green, is still tight, with quarter radius. So it only has to go a quarter, multiplicative quarter distance further. On the other hand, for our chain decompositions, we have our half step operation. So in this operation, recall we go to the middle of the chain, we delete a ball and we send it to its smaller radius neighbor. But since there are only two balls intersecting, I can only guarantee that the smaller radius neighbor has radius half of the original ball. That's why we call it a half step. So we note that in KLS, the only iterative operation they do gives them half steps, and this gives them their final approximation ratio. We want to improve on this by adding some quarter steps to our algorithm. In particular, we can show the following. Every half step we subject the client to is followed by a quarter step. And this is where our improved approximation ratio over KLS arises. Let's try to see the advantages of how to prove this. So, suppose a client, this blue one, is subject to a half step in a chain decomposition. So I delete it and send it to its green neighbor, which has half the radius. So we want to focus on what happens to this red highlighted ball. If this red ball is subject to a quarter step, well, then we're happy because our initial half step is followed by a quarter step. The thing to be careful of is, what if this red ball is subject to its own half step? Then we would be in trouble because we have a half step followed by another half step. But here we crucially use the fact that in our chain decomposition modification, we require that the ball we delete is in the middle of a chain. But let's look at this red ball right now. Previously, it was in the middle of a chain with this blue ball, but now it's at the end of a chain with this green ball on the left. So what does it mean if this red ball is subject to another half step? It must be the case that a new chain grew from this red ball so that it is now in the middle of a new chain, as in this picture. If it's subject to a half step, as following, we'll actually show that whatever ball this red ball is going to actually gives a quarter step to our original blue ball that we cared about. So this completes the proof that shows that every half step must be followed by a quarter step. So I want to note a few things about this proof, two things. The first thing is that in order to analyze this algorithm, we had to analyze the quarter steps and half steps together. We could not analyze them in isolation to achieve improvement over KLS. The second thing is we crucially use the structure resulting from our chain decomposition to show that every half step is followed by a quarter step. The reason is because we very deliberately said that we have to go to the middle of a long chain to do a half step operation. This means when we delete this red ball due to another half step, a new chain had to grow around this red ball. And this new chain is exactly what gives us the desired quarter step for our initial blue ball. So to summarize, this is how we get our improved approximation ratio over KLS. We have a half step followed by a quarter step, but KLS only does half steps. On our previous slide, we already showed that we have a constant number of fractional variables at the end of this procedure. So this is what gives us our complete improved approximation ratio over KLS for K median with outliers. So to summarize, we improved the approximation ratio of KLS by allowing a richer set of tight constraints. We generalized from one set of disjoint balls to two sets of disjoint balls. This allows us to improve the approximation ratio because we can add quarter steps instead of only half steps to this chaining procedure. And using this, we can improve the approximation ratio for knapsack median from 7 to about 6.3, and K median with outliers from 7 to about 6.9. Further, what's the technical challenge that arose from this? Well, in a long richer set of tight constraints, I lost the constant number of fractional variables. I have an unbounded number of fractional variables because I have two sets of disjoint balls. But we show that these two sets of disjoint balls actually have a chain decomposition. We can partition them into a constant number of disjoint chains. And using these chain decompositions, we're able to turn an unbounded number of fractional variables into a constant number. So there are two natural open questions resulting from this work. The first is, can we allow even a richer set of tight constraints in this iterative rounding? It's natural to ask, instead of allowing two sets of disjoint balls, can I allow three sets of disjoint balls? Will this allow me to introduce eighth steps in addition to quarter steps and farther improve on KLS? And the second is, recall that we also show that for K median with a constant number of side constraints, a constant number of knapsack constraints on the facilities, and a constant number of coverage constraints on the served clients, we can have a pseudo approximation as a 6.3 approximate. So can we turn the pseudo approximation with a constant number of fractional variables into a true approximation by rounding away those final constant number of fractional variables? So that concludes my talk. Thanks for watching. If you have any questions or comments, feel free to email me. Thanks.